Let's continue on chapter 3. Let's talk about the measure of a center variation. We already talked about the center. Now let's talk about how to measure the variation. How to measure the variation in the data set. So basically we use some index like standard deviation, variance to measure the variation. So let's first of all take a look at the definition of the standard deviation. Okay, so the range of the set of the data values is the difference between a maximum data value and a minimum data value. So range equal to maximum value minus minimum value. And because we are including the maximum and minimum value in the calculation, so range is very sensitive to the extreme values or outliers. So it's not very useful to use the range to measure the variation for the data set. And running rule for measure of the variation, we typically carry one more decimal places than the original data set. So meaning if the original data set was presenting a whole number, something like that, then the standard deviation or variance should be rounded to one decimal place. Should be rounded to one decimal place. Okay. And also just run the final answer, not a value in the middle of the calculation. So that's important. So do not run in the middle of the calculation, just run the final answer. So the standard deviation of a set of a sample value denoted by S represent standard deviation, sample standard deviation. And we also have sigma. Sigma represent the population standard deviation. So basically, standard deviation is used to measure the consistency among all data values. Okay. Also, you can say that it captures how much data values deviates away from the mean. Okay. So we have if you look at these two, precision errors and jungle errors, they have the same average, the same mean, right? And then obviously precision errors has less variation compared to the jungle error. So jungle error has more variation. Because data value varies more in the jungle error, but different variation. So the variation actually measures the consistency among all data values. Also, we use a typical formula to calculate the standard deviation. Those are the formula. We have two formulas we can use to calculate the standard deviation. Next slide, I'm going to show you how to go through these formulas. So in this formula, X represents each individual data value. X bar represents the sample mean. And an N represents representing the sample size. So you sum up the difference between each individual value and also the sample mean, square that, and dividing by the sample size minus 1, and then we're taking the radical from there. So this is the formula, first formula. Second formula is called a shortcut formula. And still, in this formula, we don't need to calculate the sample mean. So that means we have less calculation. That's why it's called shortcut formula. So less calculation. So it's more convenient to calculate the standard deviation. Although it looks more complicated, but actually it's a lot quicker to find the standard deviation. All right, so let's talk about some important property of the standard deviation. Standard deviation is a measure of the variation of all values from the mean. The value of the standard deviation S is usually positive because it's radical. So standard deviation equals square root of summation x minus x bar parentheses square over n minus 1. Because it's square root, so it's never going to be negative, it's always positive. The value of the standard deviation S could increase dramatically with the outliers, right? Or the extreme values. So if you have more extreme values, the standard deviation will become much bigger. And the unit of the standard deviation are the same as the unit of the original data values. Because it's a square root of a square, so something square, so they have the same unit. Okay. So now let's use either formula to find the standard deviation of this number of chocolate chips. Okay. So I'm going to show you both methods. First one, we're using this standard deviation equals summation of square root of summation of x minus x bar square over sample size minus 1. So this formula, we need to calculate the sample mean. So sample mean equal to summation of x by sample size. So you're going to sum up 22, add another 22, adding 26, adding 24, and divide by 4. It's 50 plus 44, it's 94 by 4. So let's see what the result is. 94 by 4. 23.5. So we have a sample mean 23.5. Now you can create a table. I'm going to put in x values 22, 26, and 24. Okay. I'm putting a sample mean here. So the table will help you organize all this and eventually come up with the proper result. Mean we already calculated is 23.5. It's the same. So first step, we're going to calculate the difference, and after that we calculate the square. So x minus x bar first, x minus x bar square. Okay. So find the difference. 22 minus 23.5 is negative 1.5, negative 1.5. 26 minus 23.5, that's 2.5. And 24 minus 23.5 is 0.5. After that, we square each one of these. 1.5 square is 2.25. Remember, after square, everything becomes positive. 2.25, second one, and then 6.25, 0.25. And if you sum up that, we come up with 2.25 times 2, adding 6.25, adding 0.25. It's 11. So if you sum up this, we get 11 summation of x minus x bar square. It's turned out to be 11. Okay, now let's apply the formula right here. Standard deviation equal to square root of summation of x minus x bar squared. We did that, it's 11, sample size minus 1. So the square root of 11 on top, so we get a sample size equal to 4. 4 minus 1. So this is radical of 11 over 3. If you put it into the calculator, run it to one decimal place, and the answer turned out to be 1.9. Okay. Alright, so this is one way to do it using the first formula. I'm going to use the second formula as well. Standard deviation equal to n times summation of x squared minus summation x parentheses square over sample size times sample size minus 1. This formula, actually you just need 2 columns. You need to know sample size and then 2 columns, which x and x squared, that's all. So we get 22, okay, 22, 26 and 24. Okay. And let's find the square square term of each one of this. 22 square is 484. 484. 26 square 676. And 24 square 576. So in this formula, it's important to calculate the total summation of x. We did that already. It's 94. And let's sum up the square term summation of x squared. And that's going to be, let's see, so adding 484 twice, adding 676, adding 576. That turned out to be 2220. Okay, so now this one you plug here. Okay, and this one goes here. And we know sample size, that's 4. So this becomes 4 times 2220 minus then 94 square, and dividing by 4 times 4 minus 1. Okay, and let's simplify that. So let's see, 4 times 2220 minus 94 square divided by 12. And that turned out, if you simplify, you also end up with radical 11 over 3. And this is exactly the same thing, same result. Okay, so definitely totally up to you. See which one you prefer to use. But the second formula is a shortcut formula, and a lot less work to do. You have to get to the standard deviation. And this is, you can confirm your answer. Okay. Next thing, let's talk about range rule of thumb for understanding standard deviation. So based on the empirical experience or principle that for many data sets, the vast majority, meaning 95% of the sample values lies within 2 standard deviation of the mean. Yes. So this is like guiding principle. 95% of data value fall in the 2 standard deviation of the mean. And according to this range rule of thumbs for interpreting a known value of the standard deviation, we can estimate a minimum usual value equal to sample mean minus 2 standard deviation. So it's like on the left hand side of the mean, a maximum usual value approximately sample mean minus adding 2 standard deviation. So this is 2 standard deviation on the left and 2 standard deviation on the right. Okay. And if you know the sample mean, you could easily calculate the sample mean using the formula, calculate the sample standard deviation. We just showed a couple formulas earlier. So yeah, that's basically what it is. So now to roughly estimate the standard deviation from a collection of the known sample data, you can just do range over 4, because maximum value is sample mean plus 2 standard deviation. Minimum value is sample mean minus 2 standard deviation. So if you expand it, you get a sample mean plus 2 standard deviation minus sample mean adding 2 standard deviation. Sample mean get cancelled, so we turn out to be 4 standard deviation. So the range is approximately 4 standard deviation. Using 4 standard deviation over 4, you get a standard deviation. Okay, that's how you make connection using the range rule of thumb and then the standard deviation given a data set. Now, using the 40 chocolate chips counts for the chips cookies. The mean is 24 chips. Standard deviation 2.6 chips. So you can just summarize that. Sample mean equal 24.0. And then standard deviation here equal to 2.6. So easily you can find a minimum usual value. By using sample mean minus 2 standard deviation. So 24.0 minus 2 times, just throw in both of them to the formula, okay, it's 2.6. So that's going to be 24.0 minus 5.2. And this is 18.8. You can also find the maximum usual value. Similarly, you just do sample mean, adding 2 standard deviation. So this is 24.0, adding 2 times 2.6. And this turned out to be 24 plus 5.2, 29.2. And the next page show you the detailed calculation. Right? And the 30 actually fall above the maximum usual value. So that's unusually high. So consider this cookie with an unusually high number of chips. Yes, so, okay. That means usual value must be within 2 standard deviation of the mean. Anything below 2 standard deviation or above 2 standard deviation is what we call the unusual values. Okay. And if you want to compare variation in different samples, to compare two sample standard deviation only when the sample mean are approximately the same. So this is good practice, right? Only when they have the same mean, then comparing the standard deviation makes more sense. And when comparing variation in samples with very different means, it's better to use a coefficient of the variation. And we're going to talk about that. It's abbreviation CV, coefficient of variation. It's used to compare different variations in different samples. Okay. And one more thing, let's talk about population standard deviation. Here's a sigma indicates population standard deviation. Measures the variation in the population. X still represents each individual data value. Mu represents the sample population mean. And then capital letter N represents the population size. Okay, so this is detailed explanation on those variables. So it functions very similarly to a sample standard deviation. When you have a population, just list out data values. You can also calculate a mu first using summation of x over capital sample population size. So you get a mean, then you can create a table like putting all the x values, then put a mu here. Now you find the difference first, x minus mu. Then after that, square it. Right? So you can create a table, calculate all these different elements like what we did earlier for the sample standard deviation, then plug into the formula to get a result. Okay, so the table is very useful. Okay, so the variance of the set of the values is measure of the variation equal to the square of the standard deviation. So variance is equal to standard deviation square. So basically, if you know the standard deviation, you know the variance. Just square it. So, or if you know the variance, you know the standard deviation. So the sample variance, we're using s square of the sample standard deviation, s. Population variance, sigma square. Again, we're using different symbols to represent sample and population. Sigma square is the square root of population standard deviation sigma. Okay. All right, so this is a relationship. Sample standard deviation, square that, you get sample variance. Population standard deviation sigma, you square that, you get population variance. Okay. They're related. So the sample variance s square is unbiased estimator of the population variance sigma square, which means values of the s square tend to target the value of the sigma square instead of systematically tending to overestimate or underestimate sigma squares, assuming we have simple random sample. And this assumption is very important. Sample is the simple random sample. Then we can guarantee x squared sample variance s square is the best point estimate of the population variance sigma square. Okay. So sample is a simple random sample. This is most important assumption to guarantee sample variance is the best point estimate of the population variance. Now let's take a look at some other concepts with respect to variation. Okay, so we have empirical rules, 68%, 95%, 99%, three different values. So for data set having a distribution that's approximately bell-shaped, meaning we have normal distribution, then the following things applies. First rule is about 68% of the data values falling one standard deviation of the mean, 95% of the data values falling two standard deviation of the mean, 99.7% of the data values fall within 3 standard deviation of the mean. Okay, so this is the typical empirical rules. Now, graphically speaking, this is 1 standard deviation from the mean, and we have 68% of data values. Assuming we have a sample size of 1,000, that means 680 data values falling 1 standard deviation of the mean. SD here represents standard deviation. And assuming you have a sample size of 1,000, right? And the second one is 95% of the data falling 2 standard deviation of the mean. So here I have 950 data values falling 2 standard deviation of the mean. And the third one is within 3 standard deviation of the mean, we have a 99.9% 0.7% of the data values, which is 997 data value, causing 3 standard deviation of the mean. And this is empirical rules showing in a bell curve. So we call this bell curve. So last concept in this video will be coefficient of variation. So we're using coefficient of variation, we're using CV to represent that. So we use the coefficient of variation to compare the variation among different data set. So coefficient of variation is very useful if you have different data sets. You want to compare the variations among different data sets. We're using coefficient of variation. Yeah, it's typically expressed as percent. So the bigger the percent, the bigger variation. Bigger the percentage, bigger the variation. So we get coefficient of variation for the sample using sample standard deviation over the sample mean times 100%. So it's like the ratio of the standard deviation to the mean, right? And then population coefficient variation equal to population standard deviation over population mean times 100%. So now one more time. This is the data set we worked with earlier. We know that the sample mean equal to 23.5. Sample standard deviation is approximately 1.9. We did it earlier. So the coefficient variation for this sample will be standard deviation over the sample mean times 100%. So using 1.9 over 23.5 times 100%. And this approximately, let's see what that is, 0.9. And turned out to be 8.1%. So the coefficient variation for this particular sample, it's 8.1%. Okay, and that's how we calculate that. Just need to know those sample mean and the sample standard deviation, find the ratio of those two.